Okay, so you have seen all these nice videos that Martin showed you towards the end, where I've seen how computers can imitate some human tasks. In the last video, it looked more like the humans were imitating the computer than the other way around, but maybe that's also how we stay economically relevant. Good. So now, how are these things done? We have learned, of course, all kinds of ways of how we do the basic task of regression and classification. And we're going to get now to one topic that's, of course, very popular, and that's to do this task using neural nets. Okay, so we'll spend, I think, the next probably 5 lectures on neural nets. That's, of course, a topic that's very hot. There's, of course, a lot of things going on. You can't open a newspaper without seeing something written about it. And, of course, like in any such thing, when you see all this huge hype, partly it's, of course, a hype, but partly there is, of course, a lot of it there. I mean, a lot of the advances in machine learning have come from knowing now how to master neural nets. The idea is not new. The idea is quite old, but it has taken quite a while until people have figured out how to use them. So now at the end of these 5 lectures, you will not be able to write a program that plays Go like a grandmaster, okay? But basic tasks like handwriting recognition or some other tasks that probably 10 years ago were considered still quite difficult, that's quite easy, okay? So you just essentially take the data, plug it into one of these modules that, these things are, of course, already programmed in these frameworks, and you will see that you can get very good results. The basic idea is very simple, right? We have seen in the past that if we do linear regression or classification, we would have our data, and then we would have this data connected via some weights. So this would be my vector x here. There would be some weights here. And so we would implement somehow the function x transpose times w. And then, depending if we're looking for regression or classification, perhaps we still add some constant in here, or perhaps we take this in the exponent if we do logistic regression. Essentially, then, that's the quantity that we are interested in, and learning corresponds to, given the data, finding the b and the weights, right? And so that's also what you did presumably in your first project. And so we have seen that in order then to have good results, a lot of things might be necessary to do first work on the data, right? So perhaps, rather than taking the original data here, which is typically, we assume, this d-dimensional, perhaps you need to add some data, right? So you need to work on the features. So perhaps you normalize, but perhaps you add some features to it. We have talked at length that, presumably, think, for example, as x being something 2-dimensional. Let's assume you have a classification task in which the function should be 1 inside, let's say something like a circle, but 0 outside. Well, if you just have given the data pairs x1 and x2 here, and that's your data, that's your vector x and the y, well, if you want to do some linear classification on this might be difficult. But if perhaps we can also add something like x1 squared and x2 squared to our features, right? Then this becomes trivial now even to do with linear classification, because with these features we can describe a circle, and now it's very easy to do, right? So, okay, so now how we do this? Well, we can add now lots and lots of features to this thing here. But how do we do this? Well, either we do brute force, we just add, we have some guess, we add maybe all polynomials to some power. Okay, what's the problem with that? Well, it becomes very quickly computational difficult. It's also not clear that maybe improves. And you can also get trouble then with overfitting and things like that. Okay? Or perhaps you ask a domain expert, and the domain expert will tell you, well, perhaps these features are more interesting, right? Or perhaps you follow maybe what Martin just says and maybe try things like singular value decomposition and principal component analysis, and perhaps that way try to find good features, right? But wouldn't it be nice if perhaps we had something that told us how to learn these features themselves, right? So wouldn't this be nice if we had maybe a box first, right? So if I had my data, and I had maybe first something that I can put this into some box, and then out of the box come maybe my features, maybe I have k features here, and then maybe after I transform these k features into a nice domain, Now I do this linear regression or classification, right? And so essentially there should be something, again, hopefully based on just looking at the data, where I can learn such feature transformation. And all this really is, right, after all, originally my data is d-dimensional, right? So this is d, this is, let's say, k. So all I really would like to learn is some function f from, let's say, r to the d into some other r to the k. And hopefully in this domain now things become simple. Right? And so, as we said, we can do this by brute force. We can do this by asking a domain expert. But now we're trying to actually learn such a function. And the neural network, all it will be such a function. And this function will be parameterized by a set of parameters. And these parameters themselves will try to learn from the data. Okay, so all it is our neural network will be a function that we're learning. And so the only kind of key or the kind of smartness in there is how do we parameterize a function, right? So for example, we could take a function, there's where some polynomial functions, and then the parameters could be, for example, the coefficients of these polynomials, right? So that, and then we could try to learn these, vary them, and learn them. So a neural net is simply a slightly different structure, something, you know, looks very graphical, something that's fairly natural. And so let's just see right away what our structure is. So again, like in anything, there are billions of versions of neural nets, flavors, variations. So we'll just look at some very basic version of it. So what will be the basic structure? Something quite simple. So we're having here our data. And this data is, of course, always d-dimensional. So we start with something d-dimensional. And since we'll transform this data, and we'll transform it over stages, and so we'll always call them this data still even to transforms one x, I need to give it some other index. And so the way we can do it is that I'll write this vector here x as maybe x component 1. And I want to say that this is the original data, so I'll give it a superscript 0. Okay, so this will be x0, the second component 0, and this will be the last component of this data, but still the original data. And so now I will slowly transform this data. And the way we will transform this data is that we'll have layers here. And so the computation will be in a feed-forward manner. And this is not the only way you can do it. There's also neural nets that are recursive, so they have a feedback. But we look right now at the simplest case. And so the computation will be from left to right. So the function will be, I'll give you a graphical representation of the function. And the idea will be that we put the data in here, and then we follow it. And you know, the final thing will come out here. And so how do I do it? Well, what I do it is I connect this thing. So think of just a complete bipartite graph here. So every node here, and so here I will have k nodes, which doesn't necessarily have to be the same as the d, could be bigger, could be smaller. And so I'll connect every single input node here to every single output node here, so a complete bipartite graph. And what I'll put on these edges will be weights. So I'll put here weights, and so I need to denote the weight, and so I'll call it wij. So if I'm connecting from node I to some node j here, then the weight will be wij. And since we'll do this over several times, I still need to tell you what kind of the layer is. And so I need to give you an index of the layer, and so I'll put an index on top here. And so the index will be to wherever I'm going to. Okay, so that's just a convention. So this will be w going from node I to node j. There will be a real number on top of this called wij. And this, since it goes to layer 1, this will be layer 1 here. Then I have a superscript 1 here. And so these outputs now, and I'll tell you in a second how we compute these outputs. These outputs here, I'll call again x, will be again x1. But now this is on layer 1. And so since I have here k nodes, this will go from x1 to xk. And this will be now on layer 1. Make sense? So now, what is the description? How do I get my x? So if I'm looking at x at layer 1, and I'm looking, let's say, at J, right? So this node J is connected to all the possible inputs. So it's just going to be a weighted linear combination of the inputs. So this means it's the sum X I J times W I J 1. So it's just a weighted sum of all the, there's no Xij, there's just Xi. So all the possible inputs, right? So I in this case, and since this is from layer 0, so I in this case goes from 1 to D here, weighted by whatever weight I have on that edge, right? And then I still have a new, another term here, and let me call this Bj1. So this, I have also a bias term that attached. So to each node here, I also have a particular bias term. Okay, so for example here, this bias term is called Bj1. Okay, so we're not quite done yet, but essentially output to first order is the linear combination of all the inputs, particularly weighted by these parameters Wij plus a bias. Now, it's not quite it, okay? So if that was it, wouldn't be very interesting. There's still some magic happening. And the magic happening is that I take a function of this. Okay, so let me just denote what these things are called. So this is called the bias term. So these are the weights of the network. These things here are called, such a thing here is called a layer, right? So I've already have a layer. And in particular, this is the input layer here. And layers that are in the middle will be called hidden layers. Okay, so input layer, hidden layers, and we'll get then to an output layer in here. And this thing here is called the activation function. Okay, it's just a name. It's just whatever function I pick here. The important thing here is that this activation function will be some non-linear function. For example, so there are many functions I could pick. Perhaps it could be something like 1 over 1 plus e to the minus x, and this looks something like, this, right? Okay, so could be something like this, and there are many other activation functions they can pick, and we'll talk about the various choices that we can have and what might be the advantage of these choices and the disadvantage of these choices at length later on. Good, so now this is just the first layer, so now we go on. So let me just take this away here. So let me write this down here. Good, so this was the first layer, and so now I go on, have various layers, and so these layers don't have to have the same width. They could all have different widths. These layers don't have to have the same connectivity pattern. We'll learn of variations where they're not all connected, they're not fully connected. These layers don't all have to have the same activation functions, but in the simplest case, assume they all have the same activation function, and it's always fully connected layers, and it's always, let's say, width k, right? So you have here the second layer, then this would be x1 second layer up to xk second layer, and again, you have a fully connected matrix here, and again, you're having weights here, and just the notation, since this goes to layer 2, again, all the particular weights you have. And again, the description is exactly the same thing as you have here, just now with the index being 2. The only difference now would be if this has width d here, but this has k, the sum would now go over k, right? So for example, now in this case, the description would be that you have x j of 2 is equal, again, the activation function applied to this linear combination here, but now it goes over k, x, I of level 1 now, all the weights going from I to the j of level 2 plus whatever bias term you have. Okay, so you go on. And so you will go on up to whatever level you have. So maybe the last level is called maybe level L. And you have x1 up to x k of L. And so then after that, let's assume it's the last internal layer. After that, you simply have your standard linear classifier. Okay, so you should think of going from here to the last hidden layer in L as simply transforming this function. Now you have a function in a different domain. So for example, this could be whatever this transformation that Martin talked about, the SVD, right? And now you have your data in this transformed domain. And now you simply apply a standard classification or regression as we had done beforehand. Basic idea clear? Yes?
So in this case, you no longer need preprocessing.
You no longer need?
Feature preprocessing.
Feature preprocessing, sorry.
Adding the x squared and this stuff, you no longer need to do that.
So, you know, you could still, so this will give you some transformation, right? Now, it's not that, you know, there's still a lot of work of trying to get this network, and we'll talk about, so what does it mean now to learn this? It means to learn these parameters B's and W's, okay, given the data, and we'll speak about how to learn it. Now, for some task, like, you know, some relatively simple task, the network in itself, given some reasonable amount of data, will learn something that's very good, will come up with very good results. But it's not a miracle cue, right? Think of that you take some data and you first transform it into some really weird domain, but in a one-to-one manner, right? Now, in principle, that's exactly the same data that you have, but it might be substantially more difficult to learn from that domain, even if you have a powerful neural net. So if you know something about the data and you know that perhaps it would be good to add that or transform it and so on, it's still good to do that beforehand, right? So these things are not mutually exclusive, but this gives you already many parameters to choose and many functions to choose, and we'll learn about what kind of class of functions it can implement. And it can implement a very wide variety of functions. But that doesn't necessarily mean it's easy to learn these functions from the data. And so if you can give it a leg up by helping it because you know you have some intuition, this might still be a very good idea. Clear? Yes?
In the last part, can we, instead of doing a standard linear classifier, can I do logic?
Yes. Yeah. So the last part is essentially you can pick anything that we have learned so far. Okay? So you should just think of the first part as some transformation of the data. Maybe the thing that you tried so far in the project by hand to do this thing, etc. Okay? So important right now is it clear to everyone that you take your vector here, and when you take the vector here, you follow these in a feed-forward manner, these computations. From this, you compute x1 vector. From this, you compute the x2. You go until you compute the xl. This is now your transformed data. Hopefully, this data is now kind of in a nicer form. Now you do your classification or logistic task here.
Do all layers have the same number of nodes? Okay.
Were you here 5 minutes ago?
Yes.
Yes? Okay. No. They can have anything. Okay? It's just you have like, there's like anything you can think of, people have tried. Okay? And probably many other things, okay, that we can't even think of, okay? People have tried anything. You can have, you know, these networks can become large, then again small, these networks can go up. These networks often have what's called, and we'll talk about many of these things. Often you don't just have one representation per layer, but even several, so vectors, okay, these are called channels. You can have different activation functions, when anything you can think of, people have done. And one thing in particular is that very often these are not fully connected. Okay, so something, for example, called convolutional. So typically you have a very local structure that implements, and we'll figure out why. Okay, so anything you can think of might be a good scheme to do. Good. So now, what do we have here in this function, right? So you can kind of see how many parameters are, right? You can see, so depending how many layers there are, right? So there's something like L layers perhaps. Then each of them, there might be, you know, K nodes. And then for each of those, right, if you take the whole thing, there might be something of order K squared parameters, right? Because you have a fully connected network in here, plus you have still the biases. So you have, you know, so this is kind of the number of parameters that you have. And so again, right, so there's of course, as in all the other cases, there will be trade-offs. The more parameters you give it, the richer the class of possible function is that you can represent. But then you might worry again about overfitting, making it maybe too rich, right? And so again, if you had, of course, some clue what kind of functions types would be good, what kind of activation functions, what kind of local structure is good, this can make a big difference. Now, just to give you some idea, so, you know, how big are these things? You know, in the past, some years ago, you know, maybe just 1, 2, 3 layers would have been a standard to do. But these days, you know, when you look at, you know, they could have hundreds of layers, these networks, okay? And so there could be hundreds of layers with literally millions of parameters that you have in here, right? So they can be very large. So unless you have a nuclear power plant and a football-sized server farm, okay, it's going to be quite difficult to train. Okay, so these things that you see in the news are typically not the things done on your iPad or laptop, okay? They're done. And so even though there's many things we can say about these networks, right? Currently there's no, let's say, complete theory that would tell you, okay, so you give me the data, I look at the data, that's the network I should pick, and then this is the way I should pick the parameters. Okay, there's a lot of what you did in your project, a lot of trial and error, trying these sizes, trying it out again, training, checking, you know, cross-validation, and you know, a lot of trial and error. There's a lot of art still involved, right? But there are also a lot of things that we can say. For example, we'll talk a lot about what kind of functions we can represent. There's very good algorithms to train. Okay, so how do you think we train? Okay, there's only one possible answer. Okay, stochastic gradient. Okay, so that's again the standard thing. And you know, in this particular setting, there's a you know, a very specific and efficient algorithm to do that, to compute these derivatives. It's something that, you know, a message passing algorithm that does a forward and backward path to compute this derivative. So to do this in an efficient manner. Okay, so essentially that's it. There's no magic to neural nets. It's just, you know, rather than taking some other way of how to specify or classify or parameterize functions, you take this particular way to parameterize functions. And learning now means taking the data, first having the kind of hyperparameters that you have to decide on. The hyperparameters would be now the width, the height, the activation function. These are the hyperparameters that you need to figure out. And once you have the hyperparameters, you need to train the data. And of course, it's not that you first train the network and then do the classification, as you train everything together in the same manner. Is that clear? Yes? Okay, so maybe still, since we have a little bit still some time, let's just maybe see and have already a peek preview of what are the questions that we will be interested in. So some of the questions we will look at is how powerful are these networks? And when I'm talking about what does it mean, how powerful, I mean what class of functions can be represented, right? So remember, what we talked about is that all this network is just a function from this d-dimensional space to this k-dimensional space. And the question is this function class a rich function class, right? So because clearly if there's only very specific functions that can be implemented, perhaps that's not very useful. And we'll see that in principle, if we don't give it them very stringent constraints of how many nodes there should be in there, that any reasonably smooth function in a bounded domain can be approximated arbitrarily closely. Okay? Now, that sounds great, okay, but all the devil is in the detail. The question is, how many nodes do I need to get some good approximation, right? I mean, it's great if I can do this with a few nodes. Of course, if I need 10 trillion, billion, gazillion nodes to do some very simple function, then perhaps it's not so useful. Okay? Now, we'll just see a few examples of how you can do this. So let me just tell you right away how we should think about it, maybe in one dimension. But maybe before, let me just state some other questions. So how do we train? And so we'll see, as we already saw, that stochastic gradient is answer. Then we'll look at some important variants. And in particular, some variants that are very important is what's called convolutional nets. Convolution nets are something very simple. Just rather than having a fully connected graph, you have a graph with a very local kernel. So people that have done signal processing, it looks like a convolution disk processing. Okay, we'll see exactly what that means. And then we'll see some basic techniques for improvement, like variance also. And in particular, how to avoid overfitting and things. So there are techniques, something like dropout, for example. These are techniques that help us, besides the standard techniques like applying some regularization term, which you can also do here, is equally easy incorporate in stochastic gradient. But there's some other techniques that are more specific to neural nets that can help us to avoid overfitting. Okay, so these are the kind of things that we'll learn, and more or less that's it. Maybe we do a few other things. So since we still have 10 minutes, let's start right away with the first question here, and let's think a little bit about what such networks can do in terms of representation power. Okay, so we start how powerful. And so let's first think of the case where we're simply thinking of a function from R to R. Okay, so we're just thinking on bounded domain. So I'm thinking of a very simple function. My input is just some R, let's say from A to B, or from whatever, 0 to 1 or something like that. And my output is also this. And then we'll slowly see how we can build things up. Okay? So, so let's assume I have just one input here. And now I have a layer of hidden nodes. Right? So I have just, and all I'm thinking about is a single such layer. So I just take this. So I have input. Let me just call it X. And then I have a hidden layer. And then after that, I'll take my output layer. So this is my output layer. And so in this particular case, so maybe this is now x0, this is x1, 1 up to x1k, and maybe this is w1. So this is, I just need one index now because I have only a single input. So this is w1 W1, and this is W1K. And then I have maybe also W's here. And again, I just need one output here. So maybe W2, and again, 1 to W2K. Okay, so I have here my bias terms, B1 up to BK. Sorry, 1K here. And then I have some activation function phi. Okay, so now the question is, let's assume I don't put any particular constraint on the width, on the k, right? And so I give you a function, some reasonably smooth function. Maybe the function just lives between 0 and 1, and I give you some function like this, and I want to see whether this function can be reasonably approximated or not with such a neural net. Okay? Any ideas how we could do it? We're not right now, we're not interested in the, how that we can do it in the best way with the least number of nodes. We just want to get some intuition of how we could potentially do this. So remember what happens, right? So if I look at a single node here, so I have the input, x. I look at a single node here. I have some particular weight. Okay, here's all I see this. I have some particular bias. And then what I see here is this phi of xw plus b. Right? Yes?
Yeah, we can divide our interval from 0 to 1 to subintervals, and on each subinterval we want one node to represent the value on this interval.
Okay, so your suggestion is let's take something like this, right? And now your suggestion is to saying that you put you always put one node in charge of doing this. Okay, so what would you, so if you forget about everything else, what would you then, what should this output look now? Let's assume this node is responsible for that output here. What should the function just based on this node? So just look at this. After you do this, you just take the sum, right? So this will just be the sum, potentially the weighted sum of these things, okay? So what would you like that to look like? One node. I mean, what should this function look like?
It's 0 if the input is not in range, and it's the value if it's in range.
And range here means what? Okay, so this means rather than, let's say, a point, right? Let's do the following, right? You all know that, Riemann integral, right? So you all know that you can approximate a function by approximating it by upper and lower sums, right? So you could take this function here, whatever, okay? And for example, you can approximate it by having something like this, right? Okay, I'm not very good at drawing, but I guess you get the point. You can approximate a function, as long as it's reasonably smooth, arbitrarily closely, by simply taking a subdivision, right? So for example, maybe you do it by just uniformly dividing this thing. And now if you want a lower sum, just take rectangles, always of a width delta. Okay, so specify some particular width delta here. Take rectangles, and then in each such subinterval, you represent this function by this rectangle here, right? And you can give me a lower bound like this, but you can do so an upper one by taking rectangles that are strictly above the function, right? And in particular, if you do an integral, that's exactly what you're doing. You're thinking of this function, either a lower one and upper one, right? Now for a rectangle, it's clear what an area means. You're taking the sum of these rectangles, you get a lower bound and an upper bound on the integral, you're taking a closer and closer partition, and if you can get converging series from the top and from the bottom that give you the same value, that's the value of the integral. With me? Okay? So we could approximate then a reasonably smooth function, so any function that's, say, Riemann integrable, right, if we knew how to get a rectangle. Is that clear? Okay, or something that resembles a rectangle, right? So, and that's indeed the first approach. Okay, so first approach. If we can approximate, doesn't have to be exactly a rectangle, but if we can approximate to any degree we want rectangles, then we can approximate any reasonably smooth, and we'll get what this means, smooth function. Because any reasonably smooth function can be written as a sum of rectangles. Okay, might need now we need to define what we mean with the approximation. Okay, so what is our error? Is it the maximum error? Is it the average error? Is this the L2 error over the interval? So we'll need to define a metric. But once I define this, you give me a reasonably smooth function. You know, with enough patience, I can draw enough rectangles, okay, to fulfill that. Is that clear? Yes? Yes?
You're trying to approximate the function of the area below the function.
No. So this analogy was just trying to connect to something that you know, namely the Riemann integral. Okay? So, I mean, the function will be a function, which will be what's called a simple function, namely a function that consists of a sum of step functions. That's how I will approximate it, right? And now we'll have to talk about how I want to approximate it in L1 norm, L2 norm, L infinity norm, okay? But I hope it's clear that if this function, you know, let's assume it's a continuous function, that I can do that with enough rectangles. And so if I could now figure out that I can approximate a rectangle with sufficient or with arbitrary precision by using a finite number of such nodes, right? Then I could maybe take whatever, the first 3 nodes to do the first rectangle, the second whatever nodes to the second one, etc. And then I simply sum it up, right? So our task is now kind of simplified to simply being able to, in between 0 and 1, you give me a rectangle, starts at A, ends at B, has height alpha. Can you approximate that rectangle? Okay? So the claim is not, right now, that that's how neural networks approximate functions. Right now, we just want to say, in principle, the network can approximate a reasonable function, because I'll give you a specific way of doing it. Now, when the network actually learns it, via stochastic gradient, etc., that's very likely not the way it will represent it. Okay? But you have proven that there is a way to represent it, and in general, there are many ways to approximate a function. Make sense? Now, is there any way that we can see that this function can represent a rectangle? Okay, we'll make it a cliffhanger, okay? You can think about it, and we'll talk about on Tuesday how to approximate rectangles.